Hey everybody, and it's been like 3 weeks, but I'm back. I'm back. I was a little busy, but now I'm back with some absolute value calculus. Basically, just doing calculus stuff, but on the absolute value function because I thought it was mildly interesting, and I also didn't have anything else to do. I could have done like equation of a circle, but that's a little boring. So we're doing absolute value calculus. So we have f of x equals, obviously, the absolute value of x, and we're going to find its derivative, and we'll integrate it the lame way, the boring way. So recall or don't recall, I'll just tell you, this can, oh my god, okay. This can be rewritten as the square root of x squared. So if we use chain rule, we can differentiate the inside, which comes out to 2x. Multiply this by the derivative of the square root of the whole thing. Rather, the derivative of just the square root of x, and we'll plug in x squared bottom 2. That's 1 over 2, the square root of x squared. Now we do this, we can cancel out the 2's, just have x on square root of x squared. But of course, if square root of, or absolute value of x equals the square root of x squared, then the square root of x squared equals the absolute value of x. So we have x over the absolute value of x. So that is our derivative, and you can confirm that that is true. But let's just plug in some values and think about the graph of the absolute value of x. So if we rather, yeah, let me actually draw out the graph first. Right here. It's not even a straight line. Straight-ish line. So if we have our absolute value of x, looks a little something like that. Touches the origin. So if we think about its derivative, if this is just the straight absolute value of x, then we know that on the positive portion here, it's just 1. So for any value, of course, we just plug in 1. We get 1 over 1. Now, while the derivative here is in fact a function, it's not just, a constant like it would be if we were looking at just a linear, or rather, part of this graph, not the whole thing. We can confirm, you put in any number, -1, -2, it still comes out to -1 or 1, which does coincide with what we see on the graph here. And let me erase this. That does bring me to the other definition that people do occasionally use. That's the absolute value of x as a piecewise function. So we can also write this as, this can also be rewritten as, I hate doing the curly brackets, I never know how to do those. But we can have x, for x just greater than 0. We have negative x for x less than 0. Of course, that also makes sense if you graph it out. Doing this does, if we differentiate it for different portions, if we differentiate it for x greater than 0, we get 1. For x less than 0, we get -1. But this does bring up a, I guess it was sort of an interesting thing. It's just, you can't really find a minimum point with the with our derivative here, because if you recall, taking the first derivative of a function, setting it equal to 0, gets us a critical point, and then from there we can use either the first or second derivative test to determine whether or not it is a minimum or maximum point. Now, obviously, that doesn't work with the absolute value of x. You would also never have to really use it for the absolute value of x, because you just tell if it's x, well, it's just setting x equals to 0 means x is 0. But if you had a more complex version, so let's say you get 2x squared minus 1, set the absolute value, you would have to set the inside equal to 0 just from this, rather than taking its derivative, because you'll end up with the absolute value of x on the bottom, and then setting that equal to 0 isn't great, because you'll be dividing by 0. So yeah, don't differentiate and try to find its minimum value. Use common sense and look at the graph, or just like set the inside equal to 0. You don't have to take its derivative. Um, Now let's integrate the absolute value of x. Let me erase all this. Okay. So if we have the integral, uh, just the integral of the absolute value of x dx. Now I'm gonna do it the lame way because unlike how I differentiated it where we use chain rule to get just a general derivative rather than considering the piecewise version of it, I am going to consider the piecewise version for this one because without doing so you'd have to use integration by parts, and I don't know how to do that. It's a really easy version of it too. Like, it's not, you don't have to do big iterations. You just, I think it's you integrate, you differentiate x and you like integrate the absolute value or something. You essentially you would get x times the absolute value of x over 2, but I don't know how to show that and I don't want to sound stupid, so we're gonna do a different version. We're gonna do integral of just x dx, and we're gonna have the integral of negative x dx. Real exciting stuff. So if you have taken like 3 minutes of a calculus course, you would have x squared on 2 plus c, and then from this one you would obviously have negative x squared on 2 plus c by the reverse power rule. Pretty simple stuff. There's nothing super interesting about this one. I just thought it'd be cool to integrate the absolute value of x. Of course you can have like like more complex functions, but for the most part that's the pretty basic version of it. And of course you can like, I guess, confirm, you can differentiate this. Negative 2 on 2, that cancels out, uses of negative x, which does coincide with their integrand here. Same thing here, 2 on 2 cancels, you get just 1, so it's x. So it does make sense, it's just not particularly interesting. And if we have the absolute value function, like just the basic parent function, if we have this, and you wanted to find the area under the curve, you could just make a triangle and do like base times height. 1/2 base times height. You don't really have to integrate like that. So but I guess if you had like more complex, this would be kind of interesting. Maybe I'll make a video on that later. I have said that a lot. I don't. So yeah, that's absolute value calculus. I just wanted to get this video out there because I was messing around with it. Didn't find anything super interesting, but I thought, better than not making a video at all. So yeah, thank you for watching.